Good afternoon, class. Welcome again back to MI210. And our next topic is simulation, which is one of the most useful applications of the population PK model development that we've been discussing so far in the course. In fact, you can make the argument that simulation is the most important application of these models. Today we're going to get started on this topic. We'll review the mechanisms for simulation in NONMEM and some of the options there. I want to discuss different levels of the simulation hierarchy and to differentiate the uncertainty in parameters versus variability in the population, and also outline some typical examples. We'll follow that up with a practice problem. So why do we use simulation? Well, there are several reasons. One is that simulation is an easy way to summarize data and concepts. And rather than carrying around all of the source data that might represent a particular concept or some observation, you can use a model and simulate from that to summarize. It allows us to interpolate between observed observations too. So if we have conditions and maybe at different dose levels and we want to understand what's going on in between, simulation is a good way to take the knowledge at the two bracketed ends of that relationship and to fill in the information in between through simulation. Simulation can also be used to extrapolate to new conditions. That's usually when we're applying the model to predict or project outside of the range of data from which the model was derived. And that's a riskier thing to do, but sometimes we have to do that because the decision about the next step often involves that sort of an extrapolation. And the important thing is to acknowledge that is a little bit more risky. There's more uncertainty associated with those types of projections, and we should reflect that. Simulation is also a useful way to express the expected range of variability in the response, as well as the uncertainty in the response or outcome. And again, those are two different things, and we'll discuss that in more detail. And of course, to judge model performance, we use simulation all the time. We'll talk about this in the next lecture, but one of the most useful model checking tools is something called a posterior predictive check or a predictive check. And that's completely based on simulation from a developed model. And then finally, simulation can be used to integrate very difficult problems that are not analytically tractable. And one of the ways to do that is to use simulation. An example is Markov chain Monte Carlo simulation in full Bayesian models. Where simulations from the posterior distribution are run in an iterative manner to generate a posterior distribution of parameter estimates. We have some different mechanisms for simulation. We might talk about a fixed parameter simulation or a Monte Carlo simulation. Sometimes the fixed parameter simulation is also known as a deterministic simulation. And that usually reflects one individual's response or a typical population response. It's not a simulation that characterizes population variability or even imprecision or uncertainty. Monte Carlo simulations, on the other hand, these are known as stochastic simulations. And they reflect an expected range of variability in the response under current model assumptions. And this is really where we start to get a powerful application of simulation. So Monte Carlo differentiates itself from deterministic or fixed parameter simulations in that they require random variability. And the way that we do that when we're using computer algorithms to simulate is that we need a pseudo random number generator. And there's a variety of these tools out there, all kinds of software packages are equipped with a pseudo-random number generator, everything from Excel to SAS and R and NONMEM. The nice functionality that we're looking for is that pseudo-random number generator can be called at multiple levels in a hierarchical distribution, just like the random effects hierarchy that we have in the population PK estimation model construct. We'd like to mirror that when we do simulation. And so you might want to have random variability at the observation level, the individual level, maybe occasion or trial level. So multiple levels are very handy there. And we also would like to be able to simulate from different types of probability distributions. Normal and uniform are very common, but things like log normal, gamma, uniform, or truncated normals, all variety of these can be useful to describe either population variability or uncertainty in a parameter. And so having access to a flexibility around the types of pseudo-random number simulation distributions is also a desirable quality. So we're going to talk about using NONMEM for simulation, although we will also mention some use of R a little bit later. And why is this useful? Well, the nice thing about simulating in NONMEM is that we can have a rapid and reliable conversion from the estimation model to simulation mode. Essentially, it's the same model structure, and all we're doing is changing the estimation options to simulation options. So we don't have to worry about the quality control step that's necessary to translate the model that we developed in an estimation tool to another tool for simulation. We also know that the distributions that we're sampling from are consistently specified. NONMEM has a robust random number generator. It uses a RAND algorithm. It can automate simulation estimation cycles as well, and you can also wrap that with something like R to control. So the random effect distributions in NONMEM, we're limited to NONMEM with normal and uniform distributions, but we can combine these to create other useful sampling distributions. So for example, we can exponentiate a normal. That gives us a log normal distribution. We can square a normal. That gives us a chi-square distribution. Or a combination of normals can give us a bimodal type distribution. And really, if you stack enough normal distributions together, you can approximate almost anything. There are also numerical recipes to simulate non-continuous distributions as well, such as distributions for count data, a Poisson distribution, or distribution for categorical data, such as a binomial distribution. So with these tools and with the numerical recipes, you can simulate pretty much everything you'd need to, although it can be cumbersome at times. But for the typical population PK simulation, that's quite straightforward, and we can simulate population variability using the built-in multivariate normal samplers that are part of NONMEM. So let's get to some of the technical detail about calling the pseudo-random number generator in NONMEM. Well, there are two calls that can be made, actually three. There are two that are made by default when you're running simulation. Those are call sim_eta, which returns a value called eta, and call sim_eps, which returns a value of epsilon. So the first one there, sim_eta, is called once per individual, indicating that we would randomly generate a single eta per subject, versus sim_eps, which is called once per observation. That's because we have a separate random epsilon associated with each observation. So it's the same frequency and hierarchy that we would use on the estimation side for estimation of random effects. The default distributions for these are multivariate normal, with a mean equal to 0 and a variance covariance specified in your $omega or $sigma. So remember, we specify the covariance matrix of the random effects, that's omega, or the covariance matrix of the residual random effects, that's sigma. This is what defines the parameters for simulation from these distributions. And in NONMEM, we can specify different starting seeds just to make sure that we want to control where our pseudo random number generator is starting, so we could reproduce the simulation at a later time point. The first seed in NONMEM is always for the default SimAda SimEps. We can also call the random number generator on our own outside of SimAda SimEps, and that's a call to random, where we would generate a random variate called R according to a seed specified here by this number, and this simply says the second seed that we specify. The distribution here is normal or uniform. The normals take on a variance equal to 1 and a mean of 0, where the uniforms are a uniform distribution along the continuous scale between 0 and 1. So you can always transform these to other distributions if you'd like, but the numbers that you're going to get out of the call to random are either going to be normal 0, 1 or uniform 0, 1. This is specified, as I said, in the second or subsequent seeds. You can have multiple calls to random. Okay. So let's get down to the details of an example. Let's say we wanted to simulate a simple fixed value or deterministic simulation to describe the mean response for a population. We don't reflect in this simulation any variability or uncertainty. It's just a simple prediction. And the way to do this, I'll show you the control scheme in a minute, but essentially we create a template data set, just as you would for an estimation data set, but we create a template data set with dosing, sampling, and covariates, all of the usual information. You can use all of the PredPP shortcuts, the ADDL, steady state, and so on, everything that you would normally use in an estimation data set. But this time, the thing that's different is that the DV column now is completely ignored when we simulate. Any value could be used there. Typically, we would just use a placeholder. Then after you have the template, that's going to define the dosing strategy and the number of points that will be simulated. So every time you want to see a simulated prediction, you need to insert a data record at that time point. This doesn't, NONMEM does not interpolate between data points to make a smooth line. It only provides a prediction at the points that you request. Next step is to enter the desired parameter estimates in $theta, just as you might use in estimation when we're setting initial estimates, except these should be final estimates. These are the parameters that you want to use to simulate. And we'll run maxeval0. Remember, maxeval0 doesn't iterate on the objective function. It just calculates the prediction at the current estimates in $theta. And essentially that's what we want to do with a deterministic simulation. And we can table out ID, time, pred, whatever values you'd like. The value in pred will be your typical value simulation or your deterministic simulation. And here's what it might look like. Here we have a single dose simulation for a typical individual in a population. The data points that were simulated are the round points. The lines are just connecting the dots. And that's your prediction under a deterministic simulation. Now, this should be quite familiar to you in this class because we've been doing this all along. Remember, every time we start a new estimation problem, we make a prediction at the initial estimates. That prediction at the initial estimates is the same thing as a deterministic simulation. It's just that we're using the initial estimates rather than potentially the final estimates from a prior estimation problem. Let's take a look at the control stream. It's called fixedsim.ctl. And it's in here. Let's see, simulation. Looks very much like a typical estimation control stream. We have the data included, PK subroutine, PK parameters, and theta specified here. It's really the same thing as an estimation data set with max eval 0. Okay, let's look at another one. What if we want to simulate individual data given estimated eta? So this is a deterministic simulation in a way, but it's deterministic based on a group of individuals for which we've already estimated the individual level random effects. So it's not a random simulation, it's not a Monte Carlo simulation. It's deterministic based on conditional estimates of the individual parameters. So this is useful sometimes if we want to characterize the variability we might expect to see if looking at the current population under new conditions. So the same individuals, if we were to apply a new scenario, what would it look like? So this is similar to what we did before. We're going to have template data records to identify all the time points and dosing schedule and so on. We'll have initial parameter estimates in $theta, $omega, and $sigma. These should be equal to your final estimates from some prior run. We're going to run estimation here. And make sure we include the individual prediction. And so we're going to run, really as part of the estimation, we're going to generate the individual deterministic simulation. In the table file, we'll include the IPRED column, which will capture the individual prediction. And what we're going to do is capture those values in IPRED where the missing dependent variable equals 1. So we'll have to take a look at this data set to review this, but what we're doing is basically appending to the observed data some additional scenarios, some additional data records. And that's done because we want to capture the information about the individual from the observed case data, but then make a projection based on those individual parameters to a new scenario. So let's look at a graphic first, and then I'll show you the data set and control stream. So here's what we're doing. The triangles here are the observed data. And what we've got is a population of individuals that were observed for a single dose. Okay, and then that population was used to estimate the parameters of that PK model for the single dose. But on top of that, and you see here that the predicted values are the blue circles. The predicted values, align pretty well with the observed data. But then there are no more observed data after 24 hours. Instead, what we have is a prediction, a deterministic prediction based on conditional estimates of a multiple dose setting for these same individuals. And the simulation is shown here where we have some peaks and troughs and a few other points that show the multiple dose scenario for the same individuals if they were administered some multiple dose regimen. Okay, this is a deterministic simulation in that there's no random variability. The random effects here are estimated based on conditional estimation from each individual's data. But it still is a simulation, and it's sometimes a quite useful way to simulate. So let's look how we do that. First, we'll look at the data set. The data set is called the control stream is ind-est. Let's take a look. man, there's a data set too. So the data set is really the key to this, because otherwise it's just a standard estimation problem. What we've got here are the usual columns, except we've used the missing dependent variable column, MDV. Remember, when MDV is 1, that indicates that there's no observation. So that's happening on the data record. And then we have some observed data up to 24 hours. MDV is 0 for those because there's nothing missing. The data are observed. But then, for the same individual, we have a sample at 48 hours and then a new dosing regimen with some additional doses. See this row 14 here? This specifies a new simulation scenario. This is not part of the experimental design that we've already estimated. This is a new scenario, 500 milligrams given every 6 hours for 4 more doses, right? This dose plus 3 more. And you'll notice then that there are sampling points, 50, 52, 54, every 2 hours here, that are all coded as missing dependent variable equal 1, meaning there's no observation there. These are missing data. We are just using those records as a simulation template. And so that's why we can get that graphic which shows us some observed data with the predictions in the first 24 hours, and then after that it's just a prediction based on the individual estimates. Okay, is that clear? Let's look at the control stream. So the control stream here is quite similar to your typical estimation control stream. We need the data set with the dummy data records. Make sure we include the missing dependent variable indicator. Subroutine, PK, and error all the same. We'll include IPRED here because that's the value that we are going to capture for the deterministic conditional simulation. And we simply run estimation here with some conditional method. Here we're using FO with post hoc. You could use FOCE, FOC interaction, and so on. And then we're going to create a table file where the IPRED value is going to contain the predicted value for each individual in this conditional simulation, which will continue beyond the range of the observed data to represent that simulation scenario of multiple dosing after 48 hours. So that's a really handy way to simulate, and sometimes we need to simulate this way because our random variability might not be reliable, but it's a very useful way to approach that problem in that case. Okay, now let's get to Monte Carlo simulation. In order to perform Monte Carlo simulation in NONMEM, we need to invoke the $simulation record, which is another control stream record. It allows us to specify the conditions of a Monte Carlo simulation, including the seeds. This first parentheses here, that's the seed for the first sample. That's the one that's used for call sim-eta and call sim-eps. We also have a second seed, which is uniform. It doesn't have to be uniform. In this case here, this is a user-defined seed, and the user, for some reason, has specified a uniform sampling distribution. We have the option to define how many subsets we want to simulate subproblems. So this is going to be 10 replicates. And there's an option here called only, or which is short for only sim, which allows us to, it's probably the most convenient way to simulate, because that means that anything we define in the control stream will be calculated according to the simulated random effects. And if we want to table out a parameter distribution as well as the prediction, then we can capture that if we use the only sim option. Okay, so it's Monte Carlo. The seed can be any number. Distributions, I remember again, are normal or uniform, and we only have the option to specify that on the second seed and later The first seed is always multivariate normal. We can use this option new, which I'll explain later, which it forces another call to SimAda or SimEps at the non-default calling interval. Only sim, remember, gives you predefined items with simulated random effects, and subproblems is the number of replicates. For more detail, you can look at the help file on simulation. And there's been a couple of changes, actually since NONMEM 6, and later, depending upon what you're using as input for simulation. And so you might want to take a look at the help file. Simulating individual data is a case where we're going to do Monte Carlo simulation, but since it's one individual, we only need one level of random effects. I'm getting an indication here that we've had a problem with audio. I don't know if that's confirmed with other users. Let me go back to $sim just for this case. Keep in mind that this is always being recorded too, so if it's an individual specific problem with audio, the recordings should not be affected. But we talked about dollar simulation, which is the control record, which allows us to simulate with Monte Carlo simulation. The seed is any number. Remember, the first seed is multivariate normal, used for SimAda and SimEps. Second and later seeds are all user-defined, and they could be normal or uniform. Only sim is an option that's quite useful if you want to derive any variable in the control stream calculated at the random effects. And then subproblems define the number of replicates of that initial data template. As I indicated, all of this is in the NONMEM help, so you might want to take a look at the NONMEM help file as well for dollar simulation. We'll see a few examples. So next, we'll talk about simulating individual data. We only need one level of random effects, the residual error. When we simulate population data, that's when we'll need two levels. So the way we do this is to create a template for the individual data with a desired dosing, sampling, covariates. The DV, again, is ignored. Every time we use dollar simulation, the DV is ignored. You can use any values in DV. Create a model control stream for the individual. Insert the desired parameter estimates. So if this is a typical individual, you might insert dollar theta would be the typical structural parameters. Dollar omega here is the residual error, and I'll show you for an individual it's a different setup. We don't run estimation now. We remove dollar estimation. We run dollar simulation, set some arbitrary seed, and use the only sim option. And then in the table now, when we use dollar simulation, the DV column is the one that contains the simulated values. Remember, before it was either pred or IPRED, but now that we're using a full Monte Carlo simulation, the DV column contains the simulated values. So let's look at a control stream. And it's quite similar to what we've seen before, but remember, this is an individual level problem, so the inter-individual random effects are commented out. There's no need for inter-individual variability. We just have a single subject. So these are individual subject parameters, or typical parameters for a given individual. And the residual error then is specified, error 1, which is now sampled in omega. Remember, this is confusing a bit because the nomenclature for the population model specified omega as the variance of the individual random effects. But when we do an individual fit or an individual simulation, omega represents the residual error. The way to remember this is that omega is always the first level of error, and then sigma is the second level of error. But this is a way to generate random residual error around an individual profile. We're going to run $sim with an initial seed, only sim, and sub equals 1. That's just one replicate. You can run multiple replicates if you'd like, but we're just going to do one replicate. And the usual stuff is included in the table. The DV column will contain the simulated data. Let's look at what that picture looks like. So you see now we've got that same dosing scenario that we looked at before, where the true values, or the predicted values, without error are shown by the red line. And then the simulated data with residual noise are included as the blue dots. So here we're simulating around one individual's profile, we're simulating some noise given our estimate of the residual variability. There's no inter-individual random variability included here. This could be useful if you needed to simulate, if you really were worried about the impact of residual error within subject, maybe for therapeutic drug monitoring reasons or other, where you're not really so concerned about differences between individuals, but really just the variability within subject. Okay, well that's our introduction to Monte Carlo. Now let's get to something that's probably the most useful. That's when we're simulating population data. So now we need a multi-level random effects model. We simulate the expected typical value and the expected variability. Okay, and the way we do this is similar to what we just did. We create a template with a desired dosing, sampling, covariates, whatever you'd like to include as the design. We need our desired estimates for simulation in theta, omega, and sigma now, because we're going to be simulating from two levels of random effects, plus we'll have some population typical value. So those values of theta, omega, and sigma should come from a prior analysis or from some prior information source. We run $sim, set a seed, an initial seed, some number of subproblems, and again use the only sim option. And in the table, we'll have a dependent variable column, which will be equal to the simulated values. And here's what it looks like. Concentration time relationship. This red line now indicates the typical population prediction for this drug, kinetics, and dose. But then we see around that the scatter of blue dots. And what we have here are multiple individuals. So we have inter-individual random effects being simulated. And within each of those subjects, we have residual random error associated with each sampling point. So we have both levels of random variability now, inter-individual and residual, and they're used to generate this overall variability that we might observe. Notice the variability seems to be a bit higher at the highest concentrations than the low concentrations, and that's because of the typical heteroscedastic variability. Our simulation model also demonstrates that. So let's look at the control stream that's in PopSim. And for this case, it's a simple data set. We're not including any covariates. We're just including date, time, and so on. A dosing schedule as well. And then we have a data set that's a population simulation data set, which reflects the sampling template that we want to use. We now include the inter-individual random effects, eta 1, 2, and 3 here. Those are described in magnitude by the omega specification here, which is diagonal, and you get a variance of about a 20% CV on each parameter. In $error, we specify the residual random effects, which are entering in the model here as an exponential relationship. This is sometimes useful in simulation because it avoids the problem of simulating negative values. And there's this little trick here called ind equals irep. Irep is an internal value in NONMEM that represents the number of the simulation replicate. We're just going to assign that to something called ind, or individual, and I'll show you why later. We specify $sigma, which is the residual random variability for this exponential distribution. $sim with a seed, only sim option, and we're simulating 100 replicates here. Well, what we're doing is actually simulating 100 individuals, because our data template is such that you have only a single subject. So in order to amplify that, we just take that single subject data template and we amplify it by however many replicates we'd like to. This is one strategy for simulating a population, and this is one that you would use if you're not so concerned about a particular trial design, but you really are just interested in demonstrating variability in the population. This is a simple way to do it. If you're doing trial simulations where you're interested in the power of a trial under a particular design of a fixed size, then you'd want to simulate your replicates of each trial with a particular number of individuals. But in this case, we're just demonstrating population variability. We're not really doing any assessments at a trial level, and so it's simple enough to just start with an individual data set as the template and amplify that by replicating multiple subproblems. In the table file, we include, well, we're going to include the no header option here, because when we do more than one subproblem, that header is appended to each subproblem, unless we specify no header. And that's handy because when you're post-processing this, you don't want to have to filter out that header. We can always recreate the header manually. And then the indicator here, or the individual indicator, IND, takes on a different value with each subproblem. So in this model, it's going to run from 1 to 100. And that means, we'll have 100 individuals simulated. We can use this IND as a marker for each individual. And then look, as always, we'll get the DV pred residuals, weighted residuals by default. In the DV column will be the simulated values. Here's the data set. And you see what I was talking about, it's just a single individual template. We don't have multiple individuals here, we're just amplifying that by replicating this individual multiple times. In doing so, though, the call to simAda is generated with each new replicate, and so the individual random effects are different with each replicate. In other words, you have a different individual. Even though the template is the same, the individual random effects are different. And of course, the residual random effects are different at every sampling point. Okay, so that's an easy population simulation. Some other topics to consider. What if you want to simulate covariates? Well, we could simulate a distribution of weight in the control stream by specifying a variable here, WT. This is just user defined. It's going to be equal to some central tendency theta 1 and some additive inter-individual variability. This would imply a normal distribution when you have an additive eta like this, a normal distribution of weight. Well, that's great, but what if there were certain inclusion criteria, or there was an issue with truncation or unrealistic values of weight? Well, how could you limit this? Well, here's one way to do that. You can include a do-while loop when you're simulating, which would allow you to simulate values only within a specific range. So, first we need to check if we're doing simulation, because NONMEM doesn't let you do these loops during estimation. So if I call is equal to 4, you're doing simulation when I call is equal to 4. weight is theta 1 plus eta 1. So there's some generation of eta that's done here by default with each new individual. And so the individual weight, simulated weight, is calculated by some fixed theta, some fixed effect plus this simulated random effect. And so we get some value of weight. Then there's a check. Do while weight is less than 20 or weight is greater than 100. So in other words, if weight falls outside of the range of 20 to 100, we're going to take a step further. We're going to call eta again. We're going to call sim eta again. The first time is just called automatically. We don't have to specify it because we're using eta here. And every time there's a new individual, NONMEM will call sim eta. But we call sim eta a second time and calculate weight again. And again, if this weight falls outside of the range of 20 to 100, we go through this loop again. And we keep calling sim eta until we get a value of weight that lands within the range. Okay, something that doesn't meet this criteria. So do while weight less than 20 or greater than 100. That means those are the ones in the extremes that we want to avoid. Until we avoid the extremes, we're going to keep running through this loop. You end the do loop and you move on. So that's how you can simulate a truncated distribution. The thing that makes this work, though, is that we specify on our seed here in $sim. On $sim we specify. I'll try to just highlight this piece. Anyway, in $sim we specify a seed, and then the word new is used. That allows us to call a new set of etas with each call to sim eta, even if it's not the default call. So by default, sim eta is only called once per individual. If we didn't have this new value here, we'd have the same eta. Every time we call sim eta, it would be the same value of eta. And that would be useless because if we're in this do while loop, it would be an infinite do while loop. By using the new option, it allows us to get a different eta for that individual every time that we call sim eta. So that's one way to simulate a truncated distribution. Now somebody's posted a question about describing the second seed, and here's an example that uses the second seed. Let's say we want to simulate a covariate that represents 3 categories. Maybe it's a treatment assignment. There's one of 3 treatments that subjects are randomly assigned to. Well, here's how we can do that. First, we're going to start by determining that we're doing simulation, I call equal 4, and new in not equal to 2. So in other words, we're going to simulate this categorical covariate once per individual. And if you look within the help, you'll find out that I call 4 means you're doing simulation, and new end not equal to 2, that happens anytime that we're at the first record for a new individual. So the first record for a new individual comes along, we want to simulate a treatment assignment. We're going to call random now. This is a user-specified call to random. The second seed is used, that's what the 2 stands for. And the variable that we're going to store that random number is R. And so let's look at the second seed now. So in $sim, we have the first seed, that's for call sim eta and sim eps. But that's not what we're using here. We're calling our own user-defined random number according to a uniform distribution. So this is creating pseudo-random variates on the scale of 0 to 1. That's why we use that second seed. We can't specify a uniform first seed. The first seed is always multivariate normal for sim eta and sim eps only. This now we're using to call for our own purposes. And we can then assign a value of R for treatment. We'll generate a value of R, We can assign treatments based on the value of R in different cut points. So if we want 3 equal categories, we might say if R is less than or equal to 0.33, that's one treatment. If R is between 0.33 and 0.66, that's treatment 1. And if it's greater than 0.66, that's treatment 2. What we're doing is we're taking that uniform distribution from 0 to 1 and slicing it up into 3 equally sized pieces so that we have equal probability of assignment. And that's how we can generate these 3 categories. You could have all kinds of variations on this theme. You could have imbalance in the assignment. You could have more categories, fewer categories. But this is a very simple way to generate those types of random variates. Another question here about the truncated simulation. I'll just scroll back. Does this apply to simulating concentration values above 0? Well, you could use this. You definitely could use this to simulate above 0. It can be cumbersome because, or misleading, because this doesn't create the same distribution that you're starting with. A truncated distribution will always have a different shape than the original underlying assumption, potentially a normal distribution. And so what you end up doing is having maybe sometimes an odd shaped distribution, although it will work to simulate concentrations that are above 0. The other thing you could do is use a residual error model that doesn't include values below 0, such as a proportional model. In actual practice, I don't worry so much about simulating values below 0. First of all, we've all in the real world, we always get censored PK data due to values that are below some sort of quantitation limit. And so if we just simulate and we happen to generate a few negative variates, of course they're not really negative, that's just the random noise that's simulating a negative value, but we know that it's below the quantitation limit, and so I would just define it as BQL. So you don't really have to constrain simulation of PK concentrations to stay positive, because it's a natural fact that you'll always have something below the quantitation limit, and you just simply assign anything below that quantitation limit, whether it's positive or negative, as BQL and treat it as such. By doing so, you maintain the true variability distribution of the residual error. If you think it's an additive with normal or proportional, by simulating and just discarding the BQL values, you're still keeping that true sense of the underlying distribution. Whereas if you resample from this truncated distribution, you tend to pile up points just above the quantitation limit or above the 0 value, and that distorts the distribution. Okay, so one more concept before we close today, and that's to illustrate uncertainty versus variability. Uncertainty represents the confidence or the precision around a parameter. So the more uncertain you might be about a parameter estimate, the less confident you would be. This has to do with the precision of estimation of the parameter or the reliability of the prior information source, and has nothing to do with population variability. What we're talking about here is how much can you count on a parameter, how confident can you be in a parameter to describe a certain part of your model, not how do individuals vary with respect to that parameter. So that's what I'm talking about with uncertainty. And so we can actually incorporate uncertainty in simulations, and oftentimes it's overlooked, but I think this is where we get into trouble with simulations sometimes, where we don't reflect the imprecision or lack of confidence in some parameters versus others which we might be very confident in. So we can implement this as a random effect, and basically at an inter-trial level. So every trial replicate can be drawn from a different value representing the uncertainty in a parameter. So now we're just adding another level to the hierarchy. We have the residual error. We have a single draw from sigma squared. At the individual level, we have a single draw of eta from omega squared. And then at the uncertainty level, we draw once from a prior distribution, and that prior distribution is a distribution of theta values or omega values or sigma values, and that's once per trial. This is very common in the Bayesian methods in literature, but we can incorporate this concept when simulating in a maximum likelihood tool like NONMEM as well. So here's a pictorial representation of what I just said. The residual variability has a random error associated with each data point. That's epsilon, which is assumed to be normal, with a variance sigma squared. And that gives us epsilon. Well, clearance, the individual clearance, is based on some individual estimate of eta, which is simulated from a normal distribution with mean zero and variance omega squared. Right? Well, that's fine, and there's some mean clearance that defines what the population mean would be with this eta. That mean is defined by some value of theta. Well, the point I'm making here is that theta and this omega squared and even this sigma squared, these are not known with 100% accuracy or precision. There's always some uncertainty around these, and we might want to capture that in the simulation. So what we can do is have another level up here, and here I'm just showing it for theta and omega, where the typical population value of clearance is distributed according, in this case here, it's exponentiated normal, where you have a mean zero and another variance psi squared here. That represents your prior uncertainty. So this distribution up here shows us that we have some knowledge of what a population value is, but there's a range, there's a distribution of values that could be used. Similarly, for the omega, we have some knowledge of what omega should be, but it could take on multiple values, and we want to reflect that in the simulation. And that's specified by something called an inverse Wishart distribution with a mode and degrees of freedom. But these are useful concepts, and so we tend to implement this, particularly when you move to the point of doing clinical trial simulations. The inclusion of the parameter uncertainty is I would consider as an essential part of the simulation. You can also simulate uncertainty in the models themselves by using parameter uncertainty. For example, combining uncertainty around certain parameters will change the shape of the model. An Emax model that has a very high EC50 approximates a linear model. So there's basically an uncertainty in the model structure there incorporated by the parameters. Or you could look at two different models and have probabilities. For example, probability of model A is 0.7, probability of model A is 0.3, and you just draw that random assignment like we just talked about for a categorical covariate, and you simulate model A if it's greater than 0.7, model B if it's less than 0.7. I'm sorry, the other way around. You simulate model A if R is less than 0.7 and model B if R is greater than 0.7. That's because model A happens with 70% probability and model B happens with 30% probability. In other words, you can incorporate uncertainty in the actual model itself. Where does that model uncertainty come from, or the parameter uncertainty? It comes from prior modeling exercises, maybe the variance covariance matrix of the estimates, maybe bootstrap parameter distributions or Bayesian posterior distributions. It comes from the review of literature for potential ranges of plausible values. Or you could even poll experts and generate distributions around those parameters as well. Yeah, the next question here is a detailed example of a clinical trial simulation. We're going to stick to these very simple simulations for now. This next example could be viewed as that, but we'll do a lot more work in trial simulations in the MI210 class, which starts in the fall. It's really beyond the scope of this class. Here's an example of how we might simulate including parameter uncertainty using NONMEM. It's pretty simplistic, but it illustrates the point. This is actually a trial simulation for a potential food effect where there was some uncertainty in what that food effect was. And so the food effect is going to be modeled as a relative F, a relative bioavailability here, with a different value. We're going to allow some range of uncertainty around that F. I'll show you how to do that. So first of all, we're setting up a counter. So if IREP equals 1 and new end equals 0, so that's the very first record of the data set. I call equals 4 is simulation. And then if, so count here is going to count the number of replicates. If the replicate's not equal to the count, meaning it's a new replicate, then we're going to simulate some value of F1. So first we start off by defining F1 as a negative value, and then we run a do while loop. So while F1 is less than 0, we can't use that, we're going to call a random number generator and generate some uncertainty around F1. So theta 2 here represents what's our best estimate of the population estimate of F1, or the population food effect, and theta 3 represents the standard deviation of the uncertainty distribution. So we're proposing a normal distribution here to describe the uncertainty around F1. And so we keep running through this until F1 is greater than 0. And then we update the count here. Calculate the variables of interest. Here we're just creating an AUC for reference and an AUC for the test. The test is the food effect. And for a whole trial here, we'll be simulating under a single value of F1. The next trial that comes along, we'll use a new value of F1. And then the next trial, we'll use a different value of F1. And so each trial will have a different value of F1, representing that we don't know F1 with complete precision or accuracy. And so we're going to simulate across a range of F1s rather than a single fixed value. Okay, so that's the idea. And so you can do this in NONMEM, and it works for a small number of parameters. But it's kind of cumbersome when you want to include uncertainty across all of the parameters. And that's where we need to use other tools. Here's the uncertainty distribution of F1 that was generated from that trial simulation. So here's a distribution of the different values of the population food effect, or the relative F under fed conditions, that were used in this series of trial simulations. So most of the trials used a value of about 0.8, but some went up to close to 1, and others were down as far as 0.6. Okay. So just a few more words then. Really when we're talking about trial simulation, and again, we'll get into this more in the next class, you might be pulling in prior information from lots of sources, POP-PK models, maybe an efficacy analysis in a different tool, maybe a model for the trial conduct, dropout, expert opinion, clinical trial outcomes, might come from meta-analysis. So you have a variety of sources here. You need to build this together. And so the case that we're making is that for the simulation tool to be flexible enough, you've got to accommodate parameter uncertainty and model differences across all of these things. And so the short of this is that we've built some functions in MIfuns now to implement this sort of simulation from the parameter uncertainty distributions, which would then allow a more simplistic implementation of that simulation from uncertainty from any source, whether it's a known parametric distribution or if we're sampling from Bayesian posteriors or bootstrap distributions, etc. That's the idea. And so a little bit of detail. This table describes some of the parametric sampling distributions that we could use, and a few examples here. But this is something that gets covered in the next class in the fall course, and we'll actually run through an example of that in the fall course. What I want you to get through in this particular topic is that there's a difference between parameter uncertainty and population variability, and if you're doing trial simulations, including that uncertainty in the parameters is essential to being able to make sense of that simulation and put it in the right context. Is it a simulation that we can really hang our hat on and put a lot of confidence in, or is it a simulation that shows a great deal of uncertainty, maybe indicating we need to conduct a new study or learn more about a particular component of the model. Okay. So I'm going to post this up to the site. There's a simulation problem for you this week, and I'm going to run through this and post the recording for this problem as well. This is a simulation problem where you already have a model developed for a PopPK data set. And there's a new formulation that comes along which has an increased bioavailability, 50% increase in relative bio. So then you're asked to simulate what's the expected population variability and the range of concentrations you might expect under a new regimen. So we've increased bioavailability, and marketing wants to see if we can increase the interval now from every 8 hours to every 12 hours. What's that going to look like? And so your goal is to do that simulation, compare the old formulation with the new formulation. And I've given you an example control stream and data set, and I'll post those up to the site. I'll also run through the example and have a recording of that available for you to look at within the next few days. Okay, so that's the end of our topic today. Just want to remind you that because of my travel schedule here, a couple of meetings that I'm attending, the next week's lectures will be available by recording, and I hope to have all of those posted by Monday, so you can actually get a head start on those. But we will not have a live lecture next week. It will all be recorded. Of course, you can still post questions through the course website. Okay, great. Well, thanks for your attention, and again, please follow up with any questions online later on, and we'll come back together for the next live lecture the week after next. Thank you.